this is going to be new. Okay? We will not have dealt with the naming of ionic compounds containing multivalent metals in Science 9, most likely, unless you had a superstar science teacher who went like way beyond what they needed to do. Okay? So here's what we need to realize about some ionic compounds. Some of the metals on the periodic table behave strangely, and they can give up different numbers of electrons. Most metals just give up, you know, like sodium always gives up 1, calcium always gives up 2, okay, and so on. But there are some metals that will give out different numbers depending on the situation. Okay, iron is one of them. Iron sometimes gives up 2 electrons, sometimes it gives up 3 electrons. Okay, so the problem here is that I could have 2 compounds that are different, but would have the same name. Okay, for example, this stuff would be iron oxide, and so would this. Anyone see a problem with it? I do. They're not the same thing. Okay? They are absolutely not the same thing. Right? They could have very different properties. One of them is rust, the other could be poisonous. That would be a big problem if you're writing a paper about the nutritional benefits of eating rust, iron oxide, and somebody reads the wrong iron oxide and dies. Okay, like, no, it's not true, but let's, you know, just for argument's sake, that could be a big deal. Okay? Okay? It's why we all have a first and a last name, and a middle name. Okay? So we can all tell each other apart. I actually once had 2 people with the same first and last name in the same class. 2 Chase Andersons. They could not have been more different. Okay? But they had the same name. Right? Exactly the same. Their middle names were different, but their first and last names were the same. Weird. Okay? It's confusing. We can't have 2 ionic compounds that are clearly different have the same name because of the ionic naming rules. So what we do is we indicate which iron is in this particular compound with a Roman numeral. Okay? So in the case of this iron oxide, this is the iron that has a 2+ charge. Iron can also have a 3+ charge. So if you look at your periodic table, if you can just call it up on your phone, okay, and look up iron's box on the periodic table, okay, you'll see 2 charges listed for it, 2 and 3. You'll see the same thing for cobalt and nickel, okay. Copper will be a 2 and a 1, okay. Manganese has got a whole bunch, but it'll only, I think, be listed as 2 and possibly 3, or 2 and 4, okay. Yeah, so they've got different. Some of these transition metals is what we call them. Okay, they have different numbers of charges, different kinds of charges, right? And so we have to indicate which one is involved. Now you're probably looking at that and going, okay, that sounds great. How do I know which one? Okay, the answer is you actually have to go backwards on your formula. Okay, so if I'm looking at, I'll just erase this one for now. Okay, if I'm looking at this particular compound here, okay, I need to figure out what charge iron had, 2 or 3, because it could be either one. Okay, so what I do is I look at my non-metal. Okay, my non-metal is only going to have 1 charge. Okay, there are no multivalent non-metals, so I can use it to figure out what the charge in the metal would be. Oxygen's charge is always -2, according to the periodic table. Since they're together in a 1-to-1 ratio, the charge on the iron has to be what? +2, because compounds always have a charge of 0. Okay, so the positives and the negatives always have to work out. That's why we do the swap and drop when we write the formulas, is so that the charge is balanced. Okay, that means this is the iron that has the 2+ charge, and so when I write its name, I write iron, Roman numeral 2, oxide. Okay, that's not the tricky part. The tricky part is remembering to do it. Okay? Lots of times people just look at a formula when they're writing the name and they forget to check whether that metal needs a Roman numeral or not. Okay? The only ones that need Roman numerals are the ones that have more than 1 possible charge. Okay? Heather.
Did you get your answer this morning?
I did.
Okay.
Thank you. Okay, so how do I tell if it needs a Roman numeral? I have to look at my periodic table, and I simply look at the box. If there's more than 1 number there where the charges are, like there is for iron, +2, +3, okay? Or is it +3 first? Anyway, okay, If it's got more than one charge there, then I'm going to need to use a Roman numeral. I don't use a Roman numeral if I don't have to. Okay? Everybody with me on that? So that's the trick, is just remembering to do it. Figuring out what the number is not the hard part.
Where's the charge on the periodic table?
On your periodic table, let's just bring yours up here. Okay, so just zoom in a bit here. On your periodic table, the charges appear here right underneath the atomic mass. Okay, so that's where you see them there. Right, so you can see iron is 3+ and 2+. They are actually listed from left to right in order of their commonality. Okay, so for iron, it is more often 3+ than it is 2+. Okay, same for like manganese, it's more often 2+ than it is 4+. Okay, so what if I have this compound instead? Let's go with MnO2. Okay. What's Mn? Manganese, okay? So this is how we're going to do this. We're just going to first off write the names out like it's any other ionic compound. Manganese oxide, okay? And then I'm going to have a look at my periodic table, okay? And I see that manganese can be a 2 or a 4, okay? So what I'm going to do is go back now to my compound and figure out which one it is, right? What's the charge on oxygen all the time? -2. But there's two of them, right? Okay? Every oxygen has a -2 charge. And there are 2 oxygens in this compound. So I have a total of how many negative charges? -4. Okay. I have only one manganese here, and I gotta balance this. So is this manganese a 2 or a 4? 4. All right, so this is gonna be manganese 4 oxide. Okay, now in case you don't know your Roman numerals, okay, you haven't watched enough Rocky movies, okay, go back and watch them all. Okay, 1, 2, 3. Okay, IV is 4 because it's 1 less than 5. 5 is V. Okay, and then you got VI 6. Okay, VII 7. VIII is 8. Okay, IX is 9 because it's 1 less than 10. And then you got X, and you're never going to need to go farther than that. In fact, you probably never need to go bigger than 4. Okay, and it's part of the reason the Roman Empire fell. It took too long to write numbers. All right. Everybody kind of following what we're doing here with the charge idea? Okay. The one thing I want you to make sure of is that you actually take the time to do it this way, where we kind of did it mathematically, because I oftentimes have people who will do this, but they'll do it like this. They'll say MnS, and they'll go, all right, I'm just going to reverse the drop and swap here. So if this was a -2, boop, that was a +2, and they think they're done. Okay, except that that's not, sorry, it's supposed to be Mn2. Okay, they just reverse the drop and swap, and they go, oh, it must have been a 2, and I'm done. Okay, reversing the drop and swap will work roughly 2/3 of the time. I like to be right all the time. I don't know what that's like. I just like to be right. I like to be right all the time, but I'm not. Okay, but in something like this, I would not do something that only worked 2/3 of the time. All right, let's try a different one here. Let's try. Let's try that one. All right, so I've got Cu, which stands for copper. Okay, S stands for sulfur, so that'll be sulfide. Okay, and copper can have which charges? 1 or 2, right? +1 or +2. Okay, I want to figure out which one it is, so I look at my non-metal. sulfur is always a -2. There's only one sulfur here, so copper must be a +2. All right, so then I can put a Roman numeral 2 here.
Do you want us to write like copper sulfide every single time with the Roman numeral? If it's there, or can we just like put the +2 with the...
No, yeah, you have to write it this way. Like this would be a naming exercise. I would put
Okay.
this thing here and say, what's the proper name of this? So I would want to see that.
Okay, yeah.
Okay. Okay, what's Mg stand for?
Magnesium.
Magnesium. What's Cl?
Chloride.
Chloride. What's my Roman numeral?
2.
Nope. Don't need one.
Oh,
Does
right, it's
magnesium
already
have more than
balanced.
one possible charge? See, what I told you was the tricky part, right? It's not the math, it's not figuring out what the number needs to be, it's whether I need to use it or not. Okay? In this case, magnesium only has one possible charge, so it doesn't need a Roman numeral. I was playing trick on you.
Is that why the going backwards only works 2/3 of the time?
Yep.
Because if you do that, it's wrong.
Well, not just for one that actually doesn't need it, but some of the ones that do need it, you can mess up. Like this one here I was showing you. If I have MnS2, right, and I just go, oh, I'll just reverse the drop and swap, this manganese must have a +2 charge, I'm going to be wrong because sulfur has a charge of
2.
+2, okay, and there's 2 of them,
Yeah.
so it's actually going to need a 4, right?
And so if you put the Roman numerals, would that just like be way off? Because it would be 4, right?
Yeah, so you just get it wrong because you have the wrong name. That's not manganese 2 sulfide, right? It's manganese 4.
That makes sense.
Okay, let's have you try a few here on your own. Let's have you try just maybe the first 6, let's say. All right, so all of these require Roman numerals. I'm not playing a trick on you anymore. Okay, let's see if you can get those figured out, and we'll walk through them in a few minutes. All right, so for number 7 here, we have polonium. And we have iodine, so it's polonium something iodide, okay? Iodine's always a -1. That gives us how many negative charges? 4. Okay, I only have one polonium atom to get rid of those with, so its charge has to be +4. Okay, and then for number 8, we've got antimony with sulfur, so antimony something sulfide. Okay, sulfur is always a -2 charge, which means we have how many negatives? 6. All right, so that means I have to get 6 positive charges out of 2 antimony atoms. So 6 divided by 2 is +3. Okay, so this is antimony 3 sulfide. Number 9, I've got nickel and nitrogen. Nickel something nitride, okay, and nitrogen is always a -3. Okay, so there's 6 negative charges here. That means I need to get 6 positive charges out of the nickel. 6 divided by 3 is 2. Nickel 2 nitride. And then we have ruthenium and oxygen, so it's ruthenium something oxide. Oxygen's always a -2, so the charge on ruthenium must be 4. Okay.
Yeah, I was really confused with that one.
On ruthenium?
Yeah.
I got a 4 here.
Look at my periodic.
Is your periodic table different?
Shows 3.
Okay, well, then that one doesn't work. Sorry, I made that one up off of my periodic table, which has a 3 and a 4 listed, so. Do we understand why I got 4?
Yeah.
Okay, as long as we understand that, okay, there's a mistake on my periodic table or something, okay? All right. Now, for molecular compounds, Okay, so we'll get into these here. Now, molecular compounds are made up of two non-metals. Actually, you know what? We forgot to do something with these. All right, there's one more thing that can happen with ionic compounds, and that is that they could involve special types of ions called complex or polyatomic ions. All right, so for example, back in junior high, you may have at some point used this stuff, CuSO4. How am I going to name that? It's got more than two things in it. Okay, well, the answer is there's a part of your periodic table that is called the table of polyatomic ions. And it's right here, right above the middle part. Okay? In there are your very common polyatomic ions. These are ions that stay together. Obviously, they have a charge because they're ions. Okay? And they have specific names. So when we're naming a compound, okay, that has a polyatomic ion in it, okay, we go to here in order to find its name. Right, so for the one I just put up, okay, I've got copper, okay, and then I've got this stuff. So I've got to look it up on the chart. Okay, so SO4 is right here, and it's sulfate. Okay, I don't have to change the ending of any of these. If I take something off of this table, I write the name exactly as it appears in the table. Okay, I don't change it to "ide" or anything like that. Okay, so this stuff is going to be copper and sulfate, and the charge on sulfate is -2. All right, that's going to be important here in a second. Okay, so copper, sulfate, but does copper have more than one possible charge?
Yes.
Yes, it does. Okay, so the charge on sulfate is always -2. How many sulfates are there?
4.
Okay. One. Okay, sulfate is SO4. That's how sulfate comes. Okay, there's 4 oxygens in a sulfate ion, but the sulfate ion as a whole has a charge of -2, and there's only one sulfate. If it was written like this, SO4 with a 2, then there would be 2 sulfate ions and 4 negative charges. Right? Everybody follow me on that? Okay? You got to treat a polyatomic ion like it's a nonmetal, essentially. Okay? It's just one piece. All right, so if the charge on sulfate is -2, what's the charge on copper? +2. This is copper 2 sulfate. Little blue crystals. Okay? You make a solution of it, the solution is a fairly bright blue color. You probably did a lab with that at some point in junior high.
So are polyatomic ions essentially just like pre-made ionic compounds?
They're not compounds, they're complex ions. Like an ionic compound still has a net charge of 0. These things have a net charge of something, usually negative. There's only one positively charged one on the chart. Okay, but that's how we treat them. Okay, so let's maybe try, see if we can do this one. It's a little bit easier. Okay, so right away, if I see there's more than 2 elements, I know I'm dealing with an ionic compound that has a polyatomic ion in it. Okay, because all the other compounds we're going to deal with only have 2 elements in it. Okay. All right, what's Na stand for? Sodium. Okay, then I got to look up OH on my table here. Go away, blue. All right. OH is right here, and it's called hydroxide. Okay, so this stuff is going to be sodium hydroxide. Do I need a Roman numeral? Nope. Sodium only has one possible charge. Sodium hydroxide is the name. That's it. All right. So naming compounds that have a complex or polyatomic ion in them is basically the same as naming any other ionic compound. Metal, non-metal. And I'm done. Okay. All right. Let's try one more. This one doesn't look like an ionic compound because it starts with a non-metal. However, I am playing a trick on look on your table of polyatomic ions and see if you can find NH4. Okay, it's right here, second from the top on the left-hand side. It's ammonium. It's the only positively charged polyatomic ion on your chart. It actually then behaves as a metal. Okay, anything that has a positive charge is a metal. So this is the only metallic behaving polyatomic ion on your chart. Okay, that's why it got listed first. It's behaving as a metal. Okay. So this stuff will be ammonium chloride. And they can get crazier than that. You could have this. Okay, is it still ammonium? Right, NH4 is still ammonium. What's NO3?
Nitrate.
Nitrate. Iodate is IO3.
Oh, yeah.
Okay, ammonium nitrate. If you've ever used one of those cold packs, you know, where you pop the little blister inside that's got the water in it and shake it up if it's cold, the crystals that are in those packs are ammonium nitrate. Okay? It is also very commonly used in crudely fashioned homemade bombs. Like when they, terrorists love it. It's in fertilizer. Easy to make bombs out of. Harder to get your hands on. Okay. So questions on the polyatomic ions? Okay. There's not much different there. It's basically like any other ionic compound. We don't have to change their name. That's basically all that's different. Okay. So for molecular compounds, okay, if I have a molecular compound, I have two nonmetals that are joined together. Now, as we said the other day when we were talking about ionic compounds, their bond involves the trading or swapping of electrons, and the bond is quite weak. In a molecular compound, the only way for these two things to get a full outer shell is to share the electron, because they're both negatively charged. Okay? They both need electrons. Neither one of them can give up an electron. They have to share it. Okay? And so because they have to share the electrons to be happy, they stay together, and the bond is really, really strong. Okay? So we call this usually a covalent bond or a molecular bond. Okay? And it results from the sharing of electrons. Okay? Water, prime example. Okay? Water has got a polar covalent bond, which means the electrons are shared, and they're shared very strongly, okay? But they're not shared equally. They spend more time hanging around with oxygen than they do up here on the hydrogen. Okay? That's why it's polar. There's kind of a positive and a negative end. Okay? But it's still a shared bond, shared electron bond. All right, so really all you have to remember, molecular compounds share electrons, strong bond. Okay, when we're naming molecular compounds, we will use prefixes in the names of molecular compounds because there is no fixed ratio for them to go together. Okay? In an ionic compound, they have to go together in a certain ratio to make the charges balance. In a molecular compound, they're never going to balance the charges because they're sharing the electrons instead. Okay? So as a result, they could go together in any ratio at all. Right? So we have to use prefixes to indicate in this compound there's 2 nitrogens and 3 oxygens, but in this compound there's 1 nitrogen and 2 oxygens. Okay? It's still nitrogen and oxygen, and the prefixes become very important. Okay? So, like we said, molecular compounds arise when 2 or more nonmetals react to form a new substance. The electrons are shared. Okay? The difference in naming is that we use these prefixes. Okay? So if I have this example here, carbon and sulfur together, how many carbons are there? 1. Okay, and there's how many sulfur? 2. So this is carbon disulfide. All right. Oh, this one's wrong. Okay, so there's 2 nitrogens and 1 oxygen in this compound. So the prefix for 2 is di. Okay, so this is dinitrogen. What's missing here? Mono, right? Dinitrogen monoxide, or monooxide if you want to write it that way. Either one would be right. Okay. Everybody okay with that? So we don't have to worry about any like dropping and swapping on these or Roman numerals or any of that kind of stuff. We just have to worry about getting the prefixes right. And just in case you don't know the prefixes, you might want to write them down. Okay, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, okay, 6 is hexa, 7 is hepta. You may have heard it was septa. You heard wrong. Don't ever say that in front of Mr. Real, who teaches chemistry. It's like a trigger. Okay? Hepta. Okay. 8, octa. Okay. 9 is nona, and 10 is deca, and you shouldn't need to go beyond that. Okay, in terms of the order of the names, okay, in whatever order the compound was written. So in this case here where we have P4O10, we write phosphorus first, oxygen second, so it's tetraphosphorus decaoxide. The second nonmetal still gets its name ending changed to I. All right, so these are molecular compounds, not to be confused with these. Why are these not considered to be molecular compounds?
So two of the same elements.
Right, it's the same element bonded together. These are called the molecular elements. Okay, the molecular elements are highlighted on your periodic table, okay, using a different color. Okay, so you can see there they're highlighted in a different color. Okay, so hydrogen is actually also a 2. Okay, it's not colored that way, but it should be. Okay, so all of these here in yellow, okay, come as a 2. Phosphorus comes as a 4, and sulfur comes as an 8. Okay, when they're in their element form. So just don't confuse them. You don't need to put prefixes on those. You don't say like octasulfide. It's just sulfur. That's the way sulfur appears. Okay, we don't say dioxide. It's oxygen. That's just the way oxygen comes. Is as a 2.
Wait, where did you get the 4 and 8 from?
From my key, also up here in the polyatomic elements, this little box at the top. Okay, it shows you it's N2, O2, F2, Br2, I2, N2, Cl2, S4, or S8, P4. Okay, so it's all up there as well. Okay. All right, so just don't confuse them. These are molecular elements. We don't change their name or add prefixes. These are molecular compounds. We do change their name and add prefixes on those. All right, I want you guys to try those. They're all molecular, okay? There's no tricks. You didn't throw in an ionic compound or something that needed a Roman numeral or anything like that. All right, so give those ones a try, and we'll go through them here in a couple minutes. All right, let's walk through a few of these. Okay, so for number 1, we've got nitrogen and iodine. So this is going to be nitrogen triiodide. Okay, how come I don't put a mono on nitrogen in this one? It comes first. Chemists have to be difficult. Okay? They need to feel superior, so they have to have a silly little rule that says you use every other prefix in every other situation except this one. Okay? So you don't use mono on the first one because the chemistry has to be difficult. Okay. So we got nitrogen triiodide. Second one, we've got carbon. Okay, and same rule. Okay, we don't need a mono on that. What's the prefix going on iodine? Tetraiodide. Technically, it should be hyphenated because tetraiodide isn't like truly the name, right? It's going to be tetraiodide. Okay? Monoxide is really about the only one we get away with that shortening on. Okay? All right, number 3. Do I put a prefix on nitrogen this time? Yes. So this is dinitrogen trioxide. Okay. Number 4, TE stands for tellurium Okay, prefix diacetyl. Okay, and then for number 5, we've got diphosphorus trisulfide. Okay, and then for number 6, we've got oxygen monosulfide. Okay, everyone doing all right with those? All right, that is where we will pick up tomorrow. Got to give you a couple minutes here to just quickly wipe down your desk. You can grab your soap bottle and a mask up first, then grab your soap bottle and paper towel there.